Welcome to Mysteries of the Universe. I'm your host, Ben Carter. In the grand theater of the cosmos, there's a subtle, yet fundamental performance that often goes unnoticed. The stage is the vacuum of space, and the players are the unseen, intangible, yet profoundly essential phenomena known as quantum fluctuations. These mysterious happenings, born in the heart of the quantum realm, are not just fleeting apparitions. They are the silent architects, the hidden movers, the invisible sculptors of the universe we inhabit. The fabric of the cosmos, contrary to our everyday experience, is not a static, unchanging backdrop. It is a dynamic, bubbling cauldron of energy and matter, where particles and antiparticles spontaneously pop into and out of existence. This ceaseless dance of creation and annihilation is no ordinary ballet. It is the manifestation of quantum fluctuations, the fluctuating energy of empty space, the primal heartbeat of the universe. These fluctuations are not merely a theoretical concept, a mathematical curiosity in the equations of quantum mechanics. They have real, tangible consequences. The laws of quantum physics predict that these fluctuations should cause tiny ripples in space-time, tiny undulations that can stretch or squeeze distances and timescales. And these predictions have been confirmed by meticulous observations of the cosmic microwave background, the afterglow of the Big Bang. Yet the story of quantum fluctuations is not confined to the esoteric domains of quantum physics and cosmology. It reaches into the heart of the matter, into the essence of existence itself. It is believed that during the earliest moments of the universe, quantum fluctuations were magnified to cosmic scales, seeding the formation of galaxies, stars, and eventually life itself. This interpretation, though speculative, is not without merit. The distribution of galaxies in the universe, the cosmic web of light and matter, bears the imprint of these quantum fluctuations. It is as if the cosmos is a giant canvas, and quantum fluctuations, the artist's brush, shaping and coloring the cosmic tapestry. The deeper we delve into the quantum realm, the more we see its footprints in the cosmos. The omnipresent quantum fluctuations, the random yet creative energy, the invisible yet potent forces, are all part of a cosmic symphony. A symphony that has been playing since the dawn of time. It is a symphony of creation, of transformation, of evolution. This symphony, this grand cosmic performance, is still ongoing. The quantum fluctuations, the silent architects, are still at work, still shaping and molding the cosmos, still playing their music on the grand stage of the universe. It is a performance that is both humbling and awe-inspiring, a performance that reminds us of our place in the cosmos and the profound mysteries that still await our discovery. The genesis of this enigmatic concept of quantum fluctuations can be traced back to the early 20th century, during the birth of quantum physics. As scientists began to unravel the mysterious world of the atom, they stumbled upon a strange and puzzling reality that defied conventional wisdom and ordinary logic. It was a world where particles could exist in multiple places at once, where they could pop in and out of existence, where they could be both particles and waves at the same time. It was a world ruled by chance and uncertainty. One of the architects of this new science was Werner Heisenberg, a German physicist, who introduced the famous uncertainty principle in 1927. This principle stated that it was impossible to simultaneously know the exact position and momentum of a particle. This inherent uncertainty, Heisenberg proposed, was not due to measurement errors or technological limitations, but a fundamental aspect of nature. In other words, the universe at its core was inherently fuzzy and indeterminate. Further explorations into this quantum realm revealed another astonishing and unsettling feature. The vacuum, the very definition of nothingness, was not truly empty. According to quantum physics, a vacuum teems with virtual particles, particles that pop in and out of existence in pairs, only to annihilate each other almost instantaneously. These fleeting, ephemeral particles were a direct manifestation of quantum fluctuations, of the inherent uncertainty and randomness of the universe. The implications of this discovery were staggering. If a vacuum, the epitome of emptiness, could be filled with such frenetic activity, then what did it mean for the rest of the universe? What role did these quantum fluctuations play in the grand cosmic symphony? The answer to this question came from an unexpected quarter, the field of cosmology. In the 1980s, cosmologists Alan Guth and André Linde proposed the theory of cosmic inflation, a theory that provided a plausible explanation for the structure and evolution of the universe. According to this theory, the universe underwent a rapid, exponential expansion in the first fractions of a second after the Big Bang. This inflationary period magnified the quantum fluctuations in the early universe to cosmic scales, seeding the formation of galaxies and large-scale structures. Thus, the seemingly abstract and esoteric concept of quantum fluctuations found a tangible and profound relevance in the real world. The randomness and uncertainty at the heart of the quantum realm, it seemed, were the creative forces behind the birth and evolution of the universe. The silent architects, the invisible painters, were not an anomaly or aberration, but the essential and integral part of the cosmic symphony. The concept of randomness as a driving force in the universe isn't a modern invention by any means. Ancient cultures were well aware of the role of chance and uncertainty in the cosmos. Ancient Greeks, for instance, had a goddess named Tyche, the deity of fortune and chance. They believed that Tyche governed the good and bad luck that fell upon cities and individuals. In a similar vein, the Roman equivalent of Tyche, Fortuna, held sway over the random happenings of life. In these ancient worldviews, chance and randomness were not seen as aberrations but as fundamental aspects of existence, a sentiment echoed in the quantum realm's intrinsic uncertainty. However, the transition from mythology to science was not a simple one. It took centuries of philosophical debate and scientific investigation to arrive at our current understanding. In the realm of science, the idea of inherent randomness was largely absent until the 19th century. Scientists like Pierre-Simon Laplace envisioned a deterministic universe, where if one knew the position and velocity of every particle at a given time, one could predict the future and retrodict the past. This deterministic worldview, however, was challenged by the advent of statistical mechanics and thermodynamics, which introduced the concepts of probability and randomness into physics. The quantum revolution of the 20th century took these ideas a step further. Quantum mechanics, with its inherent uncertainties and probabilities, proposed a universe far removed from Laplace's deterministic vision. Quantum fluctuations, in fact, were a direct challenge to the deterministic worldview, revealing a universe that was fundamentally indeterminate and unpredictable. The theory of cosmic inflation, proposed by Guth and Linde, provided a bridge between the microscopic world of quantum fluctuations and the macroscopic world of cosmology. This theory suggested that the universe we inhabit, with its myriad galaxies and vast structures, owes its existence to the randomness and uncertainty of quantum fluctuations. This idea was, and still is, revolutionary. It suggests that the universe, in all its complexity and grandeur, sprung from the inherent uncertainty and randomness of the quantum realm. In other words, the universe as we know it owes its existence to quantum fluctuations, to the ephemeral particles that pop in and out of existence in the vacuum. This idea, as radical as it may seem, is a testament to the remarkable journey of understanding that humanity has embarked upon, from attributing the randomness of the cosmos to deities of fortune and chance, to uncovering the quantum roots of cosmic evolution. The exploration of the quantum world and its link to the cosmos is a journey marked by the brilliance of a few pioneering minds. The first of these visionaries was Max Planck, a German physicist who in 1900 proposed the idea of quantized energy levels. This marked the birth of quantum mechanics, a theory that would redefine our understanding of the universe. Next was Albert Einstein, whose work on the photoelectric effect further cemented the quantum theory. In 1917, Einstein proposed that energy could be transferred in discrete packets, or quanta, a radical idea that laid the groundwork for the concept of quantum fluctuations. In 1927, Werner Heisenberg introduced his uncertainty principle, a cornerstone of quantum mechanics. Heisenberg's principle suggested that it was impossible to accurately measure both the position and momentum of a particle at the same time. This inherent uncertainty, a fundamental aspect of the quantum realm, would later prove crucial in understanding quantum fluctuations. The bridge between the quantum world and the cosmos was built by George Gamow, Ralph Alpher, and Robert Herman. In the 1940s and 1950s, they proposed that the universe began in a hot, dense state, an idea that would evolve into the Big Bang theory. Gauss's team also predicted the existence of cosmic microwave background radiation, an afterglow of the Big Bang, which was later discovered by Arno Penzias and Robert Wilson in 1965. However, the Big Bang theory had its shortcomings. It couldn't explain why the universe appears so uniform on large scales, or how distant parts of the universe could have come to be at the same temperature. This conundrum, known as the horizon problem, was addressed by Alan Guth and André Linde, who in the 1980s proposed the theory of cosmic inflation. This theory suggested that the universe underwent an extremely rapid expansion shortly after the Big Bang. The tiny quantum fluctuations that existed before this inflation were stretched to cosmic scales, seeding the large-scale structures we see in the universe today. The theory of cosmic inflation was a leap forward, but it was also controversial. It was criticized for being untestable, as the evidence for inflation, such as the patterns of cosmic microwave background radiation, could also be explained by other theories. Despite these criticisms, cosmic inflation remains one of the leading explanations for our universe's large-scale structure. This journey of discovery, from Planck's quantized energy levels to Guth and Linde's cosmic inflation, has led us to a profound realization that the universe we inhabit may owe its existence to the random, unpredictable energy of quantum fluctuations. This idea, as audacious as it is astonishing, stands as a testament to the power of human ingenuity and our unending quest to understand the cosmos. Delving deeper into the cosmos, we encounter anomalies that seem to defy not just our understanding of quantum fluctuations, but also the very fabric of reality itself. The curious case of dark energy exemplifies this paradox. Observations of distant supernovae in the late 20th century revealed that the universe's expansion is accelerating, a phenomenon attributed to the mysterious force termed dark energy. The prevailing theory is that dark energy is a product of quantum fluctuations in empty space, where particles and antiparticles spontaneously form and annihilate each other, creating a net energy that pushes space apart. Yet, calculations of this energy from quantum theory overshoot the observations by an astounding factor of 10 to 120, a discrepancy referred to as the cosmological constant problem. Equally puzzling is the enigma of dark matter. Galaxies rotate at speeds that should tear them apart, if only the gravity from visible matter were at play. Astronomers believe that unseen dark matter provides the extra gravitational pull to hold galaxies together. Yet, despite exhaustive searches, no dark matter particle has been detected, and its nature remains elusive. Then there's the question of quantum entanglement. This principle, described by Einstein as spooky action at a distance, allows particles to instantly affect each other's state, no matter how far apart they are. This challenges the established notion of locality, where an object is only directly influenced by its immediate surroundings. Perhaps the most baffling of all is the multiverse theory, an offshoot of inflation, which posits that our universe is but one of a potentially infinite number of universes, each with different physical laws. This challenges the very concept of a single, unique universe and raises profound questions about the nature of reality. These anomalies seem to defy conventional explanations and pose significant challenges to our understanding of the universe. While they can be unsettling, they also represent tantalizing clues, pushing us to dig deeper, expand our theories, and perhaps uncover new truths about the cosmos and our place within it. Each mystery, each unexplained phenomenon is a beacon in the endless expanse of the cosmos, guiding our journey through the quantum realm and beyond in the quest for understanding the origins of the universe. In the quest to understand these cosmic enigmas, a multitude of theories have emerged, each grappling with the paradoxes and puzzles that quantum fluctuations present. Among the mainstream explanations, one of the most prominent is string theory. In this model, particles are not point-like, but instead tiny, vibrating strings. String theory offers an elegant resolution to the conflict between quantum mechanics and general relativity, the other major pillar of modern physics. Yet despite its mathematical beauty, string theory is yet to be confirmed by experimental evidence, and some critics argue that it may not even be testable. Another mainstream explanation is loop quantum gravity. This theory proposes that space and time are not continuous but are instead composed of tiny, discrete loops. Like string theory, loop quantum gravity attempts to reconcile quantum mechanics with general relativity, but it does so in a radically different way. While it too lacks experimental confirmation, its proponents argue that it offers a more concrete, less abstract approach than string theory. On the fringe, there are theories so radical that they challenge not just our understanding of the cosmos, but our most fundamental assumptions about reality itself. One such theory is the holographic principle, which suggests that our three-dimensional universe is actually a projection of information stored on a two-dimensional surface at its boundary. This mind-bending concept, drawn from the strange world of black hole physics, has yet to find widespread acceptance but continues to attract interest due to its potential to resolve the black hole information paradox. Another fringe theory is the many-worlds interpretation of quantum mechanics. This proposition posits that each quantum event spawns a multitude of parallel universes in which every possible outcome occurs. While this theory offers an enticing resolution to the quantum measurement problem, its implications, namely, the existence of countless parallel realities, are so radical that many physicists find it difficult to embrace. Moreover, the cosmic debates engendered by these theories delve into profound philosophical questions. If the universe is a projection, what does that mean for our concept of reality? If there are infinite parallel universes, what does that imply about our sense of self and individuality? And perhaps most fundamentally, if quantum fluctuations can create something from nothing, what does that say about the nature of existence itself? These questions, while daunting, are integral to our ongoing quest to decipher the cosmos, and the answers, however elusive, may hold the key to our deepest understanding of the universe and our place within it. Peering into the annals of history, there is a curious interplay between these cutting-edge theories and the cosmological beliefs of our ancient forebears. The concept of quantum fluctuations, the idea that the cosmos was born out of nothing more than a random burst of energy, finds echoes in the creation myths across various cultures. To the ancients, the universe sprang forth not from a singularity, but from a cosmic egg, a void, a vast sea, or a primordial pair of beings. In the ancient Egyptian cosmology, the universe was birthed from the primordial waters of Nun, a personification of chaos and infinity. This mirrors the quantum concept of energy fluctuations in a seemingly empty space, sparking the creation of the universe. Similarly, the ancient Greek myth of chaos, the unfathomable abyss that was the genesis of everything, resonates with the concept of the cosmic vacuum where quantum fluctuations occur. The many-worlds interpretation of quantum mechanics, with its near-infinite parallel realities, finds a mystic parallel in the Hindu cosmology. The ancient seers of India envisioned a multiverse long before modern science. According to the Puranas, there are countless universes, each one born from the cosmic lotus flower that sprouts from Lord Vishnu's navel, who himself rests in the primordial ocean. Each universe exists for a cosmic day, at the end of which it dissolves into the ocean, only to be recreated again. The holographic principle, the idea that our three-dimensional reality is a projection of information on a two-dimensional surface, bears striking resemblance to ancient shamanic beliefs. Many indigenous cultures believe that our reality is only an illusion or a dream, and the true reality can be accessed through altered states of consciousness. These connections are not to suggest that ancient cultures had an understanding of quantum physics, but rather to highlight the shared quest for comprehending the cosmos. The human fascination with the origin of the universe and the nature of reality transcends time and civilization. It's a thread that weaves through our collective consciousness, tying us to those who first looked up at the stars and wondered. As we continue to probe the mysteries of quantum fluctuations and their role in the cosmos, we find ourselves not just at the vanguard of scientific discovery, but also in the heart of a timeless human tradition. In the ceaseless quest to unravel the enigmatic nature of the cosmos, modern technology has become a vital tool, pushing the boundaries of what we can observe and understand. Telescopes, satellites, and space missions are at the forefront of this exploration, reaching into the farthest corners of the universe and probing the deepest mysteries of quantum fluctuations. The Planck satellite, launched by the European Space Agency in 2009, has been instrumental in mapping the cosmic microwave background, the afterglow of the Big Bang. This map has given scientists detailed insight into the universe's infancy, revealing slight temperature differences that indicate regions of varying density. These regions are thought to have originated from quantum fluctuations, providing some of the most direct evidence yet for their role in the formation of the cosmos. Meanwhile, the Laser Interferometer Gravitational Wave Observatory, LIGO, has detected the elusive gravitational waves, ripples in the fabric of space-time caused by violent cosmic events. These detections not only confirm Einstein's prediction in his theory of relativity, but also open up a new way of observing the universe that could potentially reveal more about quantum fluctuations and their effects on cosmic evolution. Quantum computers, still in their infancy, hold promise for unraveling the enigmatic quantum world. They use quantum bits, or qubits, which can exist in multiple states at once, mirroring the strange quantum principle of superposition. This allows quantum computers to solve complex problems much faster than classical computers and could potentially simulate the quantum fluctuations that led to the birth of the universe. Ongoing research into dark matter and dark energy, substances that remain a mystery yet constitute approximately 95% of the universe, also hold keys to understanding the cosmos. It's hypothesized that quantum fluctuations may be responsible for the creation of dark matter in the early universe, and that dark energy is a manifestation of the energy inherent in empty space due to these fluctuations. While the mysteries of quantum fluctuations are far from fully unraveled, the advancements in technology and ongoing research continue to shed light on this elusive phenomenon and its role in creating the cosmos. Unseen, unheard, these minute fluctuations in the voids of space have choreographed a cosmic dance of creation, a testament to the hidden order in what appears to be randomness. This profound quest, at the intersection of science and philosophy, continues to unfold, revealing the intricate tapestry of the cosmos woven by the threads of quantum fluctuations. The understanding of quantum fluctuations and their implications has the potential to fundamentally reshape our conception of life, existence, and our place in the cosmos. The traditional narrative of creation across various cultures often speaks of a divine force or entity breathing life into existence. However, quantum fluctuations suggest an alternative narrative where the universe springs into existence from the randomness inherent in the quantum realm. This moves the concept of creation from the purview of the divine into the realm of the scientifically explainable, albeit still profoundly mysterious. Yet this understanding does not necessarily negate the spiritual or philosophical dimensions of existence. Rather, it can enrich them by adding another layer of complexity and wonder to our understanding of the cosmos. The idea that our universe, with its galaxies, stars, planets, and life, could emerge from random fluctuations in a quantum field can instill a sense of awe and reverence, akin to spiritual or religious experiences. Moreover, the notion that quantum fluctuations could have given birth to the universe also has implications for our understanding of consciousness. Some theorists have proposed that consciousness might be a fundamental aspect of the universe, much like space and time. Could it be that the same quantum fluctuations that gave rise to the universe also sparked the first primitive forms of consciousness? The concept of quantum superposition, where a particle can exist in multiple states simultaneously until observed, also has parallels in our conscious experience. Just as a quantum system is a blend of multiple possibilities, our subjective experience is a synthesis of multiple sensory inputs, thoughts, and emotions. Furthermore, if quantum fluctuations have led to the creation of our universe, this could imply that countless other universes might exist, born out of their own unique quantum fluctuations. We are then not just inhabitants of a singular universe, but potential citizens of a vast multiverse. This concept, while currently speculative, can radically transform our perspectives on life, existence, and our place in the cosmos. As we delve deeper into the quantum realm, it becomes increasingly clear that the line between science and philosophy, between the physical and the metaphysical, is not as rigid as we once thought. Quantum fluctuations, the invisible and silent maestros of the cosmic symphony, invite us to re-evaluate our understanding of existence, to marvel at the profound mystery of creation, and to grapple with our place within this vast, intricate cosmos. It is a journey of discovery that transcends the boundaries of science, nudging us into the realms of philosophy, spirituality, and perhaps the very essence of what it means to be human. In the grand scheme of the cosmos, against the backdrop of celestial symphonies and cosmic phenomena, we are but infinitesimal specks. And yet, within us resides a spark of consciousness, a yearning to understand, to explore, and to decipher the secrets that lie beyond our grasp. Our existence, born out of quantum fluctuations, is a testament to the profound interconnectedness of all things, an interconnectedness that weaves together the fabric of reality, from the tiniest subatomic particles to the vast, unending cosmos. The human endeavor to comprehend the cosmos mirrors our own internal quest for self-understanding. The more we delve into the quantum realm, the more we are confronted by the enigma of our own existence. We stand on the precipice of a vast cosmic abyss, peering into the unknown with a mix of trepidation and exhilaration, armed with nothing more than our curiosity and the accumulated wisdom of our species. Perhaps we are destined to forever grapple with these questions, to eternally wrestle with the enigmas of existence. Yet, it is this very quest, this ceaseless striving for understanding, that defines us as a species. Each new discovery, each new insight into the workings of the cosmos illuminates not only the universe around us, but also the universe within us. As we continue this cosmic voyage, it is important to remember that our journey is not solely a quest for answers, but also a process of self-discovery. The universe, born out of quantum fluctuations, is not just a realm to be explored, but also a mirror reflecting our deepest aspirations, fears, and curiosities. In the vast cosmic arena, we are both spectators and participants, witnesses to the grand cosmic play and actors within it. Our existence, born out of quantum fluctuations, is a testament to the profound mystery and beauty of the cosmos. As we journey further into the quantum realm, we are not just exploring the universe but also exploring ourselves, our consciousness, and our place in the cosmos. The universe, with its quantum fluctuations and cosmic symphonies, invites us into a dance of discovery, a dance that intertwines science, philosophy, and spirituality. It invites us to transcend the boundaries of our understanding, to gaze into the cosmic abyss with a sense of wonder and humility, and to embark on an eternal quest for truth, a quest that will forever shape our understanding of the cosmos and ourselves. In this cosmic dance, we are both the dancers and the dance, participants in a cosmic performance that is as mysterious as it is beautiful. Thanks for listening. This has been Mysteries of the Universe. If you enjoyed today's episode, be sure to follow us wherever you listen to podcasts. And if you'd like to support the show, subscribe to the Forbidden Knowledge Network on Patreon. Subscribe now.